we talked about, of course, a fundamental problem in quantum mechanics, one where quantum optics has been the forum where that's really been put to the test, why we're discussing it here in this context. And that is the question of decoherence. Decoherence is a physical phenomenon. It has nothing to do with the question of the interpretation of quantum mechanics, which might play a role in how we reconcile some of our fundamental issues and questions about the difference between the quantum world and the classical world. But regardless of where you stand on what role decoherence has to answer that fundamental question, decoherence happens in a sense, meaning it has physical implications. There are experiments you can do, and we'll talk about one of those today. And we typically think about it in one particular context, or what in quantum optics we call a Schrödinger cat state. I mean, that's a loaded term, but it means this. It means a coherent superposition of two coherent states of the harmonic oscillator. And we think about that as a Schrödinger cat state when these two coherent states are macroscopically distinguishable, okay? So that they represent two coherent amplitudes that are very, very, very well separated, okay? And the state of this system is a superposition state. It has diagonal and off-diagonal elements with respect to these different coherent states. And the act of decoherence is the act by which these off-diagonal elements damp. Okay? And what we showed last time, just based on an analysis, we did a couple of different analyses. One, we just looked at the Fokker-Planck equation, which represented damping and diffusion. And what we saw were that the diffusion terms wiped these off-diagonal elements out very rapidly. And the rate at which that happened was given by this expression. If gamma was the damping rate of energy, that is the rate at which energy decays out of the cavity, then we had the decoherence rate was enhanced by this factor. And that factor, if we looked at it from the point of view of, say, we thought about alpha 1, alpha 2 as real amplitudes, just doesn't really make a difference whether they're complex or real. They're separated by, in phase space, we'll call it along the x-axis, but it could be along any axis as x, and we write that in terms of physical back in first hand mass of particle, then this rate of decoherence is enhanced by the ratio of this difference, so delta x here, let's just say alpha 1 is equal to x1 and alpha 2 is x2, so delta x is the difference between them in, this is in physical units, delta x in position, these are in dimensions units. So this is putting the dimensions back in. Then this ratio we see here depends on the ratio of the separation between my dead and alive states, and whichever is the dominant term here. Okay, so if I'm at zero temperature, where the de Broglie wavelength is infinity, and this term is in here, and bar is 0, we still get decoherence. And that decoherence rate depends on the separation of the wave packets compared to the spread of the wave packets. So I would think about two wave packets, each of which has a spread of say, the simple harmonic oscillator Gaussian type spread, and delta x here is the difference between these two. And when that's big, that difference between those enhances the decay rate. If I'm at have a finite temperature bath, well, then the decoherence is even faster, and that rate is enhanced depending on what the de Broglie wavelength is associated with a particle of mass m at the temperature T. And so what we showed is this can be incredibly fast. And the point was, what's different about decoherence versus the decay of energy out of the system is that if only one photon leaks out of the cavity, that's enough for me to distinguish these two states. And when I have a macroscopic number of photons, my rate of decay is n times faster, where n is number of photons. Whereas, so if I have 10 to the 18 photons, it's 10 to the 18 times faster than the actual decay rate. And that makes decoherence happen very, very, very quickly for macroscopic systems. Okay. So what one thing I meant to talk about last lecture, but then I forgot, so let me remember now, is to tell you about a particular physical situation whereby one can create such a state and test this analysis to show that indeed that kind of superposition decays extremely rapidly at a rate that depends on the separation between these different coherent states. There have been a number of experiments of this sort, particularly by our friends, the two Nobel Prize winners from 2012, Dave Wineland and Sergei Roche. That was one of the reasons they were in the citation, which they got the prize for demonstrating this kind of thing. Let me tell you about the experiment out of the Roche group in the cavity QED realization. It's kind of equivalent to what was done in the ion trap. And it builds on stuff we talked about last semester. Let's remind ourselves, let's say we have a very high Q cavity, ultra high Q cavity, and we can send individual single atoms through this cavity. And then you remember from our analysis and studies last semester that this system is described by the James-Cummings model, right? And the James-Cummings model is the coupling of that two-level system to the single-mode harmonic oscillator. And if in particular, so the cavity has some cavity resonance, there's some atomic resonance frequency between the Mie excited and round states. And what we studied last semester was that we can diagonalize the joint energy eigenstates of the atom with the harmonic oscillator, and we get the James-Cummings ladder, right? So we have, if we're detuned, and say we're detuned to the red, so the cavity has a slightly lower frequency than the atom, then we end up with this kind of ladder of states in the rotating frame, where we have this splitting induced by the cavity. This splitting is delta, and this splitting here is the square root of delta squared plus 2g squared, where g is the coupling constant between the two-level atom and the cavity, and then we get this and generally speaking, for the nth, if we have n excitations in the system, then the splitting between these two is the square root of delta squared plus n to g squared. Right? That was our James-Cummings ladder. Okay, so here's the idea now. Suppose, so what I'm going to do is a kind of Ramsey experiment. You remember Ramsey. And in particular, what we're going to do is create a superposition of the excited and ground state and put it through this cavity. Now, when we did this, when we studied this last semester, we studied this in the case where we say had no photon, or we had one photon in the cavity, or none, and we looked at vacuum-Rabi oscillations, right? But now let's suppose that we have a microwave antenna, and we shine into the system some coherent state, right? We studied the kind of collapse and revival of this problem we started, but let's just look at this for a very particular time interval, okay? So here's the idea. I create the atom through I have a Ramsey zone over here, and I create a superposition. I do a pi over 2 pulse, and I create a superposition of the excited ground state. And the cavity has a coherent state with a particular amplitude because I shine in with a microwave horn a certain amount of microwave energy into this cavity. Okay? It's a coherent state of microwave photons. This is Rydberg atoms spaced by some gigahertz of energy. Okay? Or frequency, whatever you want to call that. Okay, so this then is equal to if I express this in terms of the Fock basis, alpha itself is a superposition of Fock states with coefficients that we know. Alpha to the n equal to minus alpha squared over 2 over square root of n factorial, right? That's the usual superposition of Fock states that leads to coherent state. Okay, so this is the state right before the atom enters the cavity. Now the atom enters the cavity, and it's detuned from resonance. And it enters slowly enough so that it starts, these are the energy levels with no coupling, and adiabatically I follow each of these energy levels in the ladder. Okay? There's no Rabi oscillations, no vacuum Rabi oscillations, when the detuning is sufficiently big and the motion is sufficiently slow that I adiabatically follow. So I get a AC Stark shift or a light shift, a quantized light shift on each of these levels. And so what happens is that each one of these states picks up a phase. All right? So, so what is that phase? Well, when the detuning, let's assume the detuning is very big, compared to n, or square root of n times 2g for all n of interest. Okay? So, because of course this falls off ultimately in alpha is some number that's not too big, and then n factorial eventually kills this. Okay? So my tuning is sufficiently big that I can expand that. Then my phase is the following. My delta for energy, well, let's say if I have G atom in the ground state with n. Remember, G means two different things. G means the coupling constant, also means state. Didn't invent that notation, but I'm using it. Then this is equal to the light shift, which is square root of n 2g squared over 4 delta squared. That's like omega squared, I'm sorry, over delta. Omega squared over 4 delta, the light shift, right? Which is n g squared over delta. Okay? And similarly, for E, with n, now we get a prop is n minus 1 g squared over delta. Or delta with n is no, sorry. What did I do? N with n minus 1. N plus 1. Because I have to couple Gn with the n minus 1. So this is n plus 1 g squared over delta. Okay. So what we find is that this is then equal to something interesting. Notice if I exponentiate this, I get something to the power n. That combines with alpha to the n. So what I find is the following. This thing becomes 1 over root 2 e to the I phi e n alpha e to the minus phi plus g alpha e to the plus I phi, where phi is equal to, this is the energy shift. I have to, the phase shift is this times time, of course. Energy times the time units of h bar is the phase shift, is g squared over delta times time. Now, you might have thought that was a big sleight of hand. Takes a little bit out. It's not much. All I'm doing is I'm taking this exponent and putting it in here, combining this with alpha, and I get an e to the I phi to the power n. Do you see that? Yeah.
How do you get a minus phi in the next way?
Oh, good question, because I screwed up. Because this guy is minus. Remember, one goes up, one goes down. Thank you. I messed that up. All right, so if I'm ready tuned, the excited state gets shifted up, and the ground state gets shifted down. Indeed, that's key. Thank you. So, this actually is kind of more akin to the actual Schrodinger cat type experiment, where I can think about E and G as the nucleus that causes the poison to kill the cat, as either being undecayed or decayed, and this being alive or dead, where I have an entanglement between the atom and the alive or dead state. Okay? Now, of course, how distinguishable these are, how short or catty this is, depends on how big is alpha and how big is this phase. I mean, what's happening here is I start with a coherent state, say, for example, with, I'll just call it initially having 0 phase, and then the coherent state is rotating either clockwise or counterclockwise depending upon its interaction with the atom. The atom causes a kind of index of refraction that's different depending upon whether the atom is in the excited state or the ground state, and causes a phase rotation differently. And so there's a phase this way and a phase that way, correlated with whether the atom is in the excited state or the ground state. Okay? And the degree to which this is a Schrodinger cat state depends on how big is that phase and how big is this initial alpha. Of course, the bigger the alpha is, the bigger the lever arms, even a tiny phase difference will cause these things to become macroscopically distinguishable. If I start with something with just like a couple of photons in it, it takes a lot more of a phase rotation to do that. Okay. Now, what we can also do is create a state more akin to the one that I discussed at the beginning of the class in last lecture, where I have a superposition of 2 coherent states that are not entangled with the atom. And that's simple to do. All one has to do is put a second Ramsey zone. It's like putting the Hadamard at the end of your quantum circuit to turn your phase kickback into your amplitude. For those of you whose that language makes any sense. But the point here is that I can, if I just put another superposition on this thing, and then I send E to E plus G, and G to E minus G, then the state afterwards in that case is correlated with the positive parity cat with a plus sign in between, correlated with E, and the negative parity cat with the minus sign correlated with G. Okay? Factor of 2 maybe. I didn't do it. And so if I measure the atom afterwards, I have a detector here, and if the detector goes click and I get only, it goes click, say only if it's an E, or I can distinguish E and G. I have a detector that somehow can tell the difference between these 2 Rydberg states. Then post-selected, based on E, I have projected the cavity into the Schrodinger cat state. Okay? And then I can probe the cat with what Luis Davidovich called the quantum mouse, which is to go back in and do a second Ramsey experiment and see how much, what that coherence is, if that coherence is still there or not. Let me show you the data.
So,
yeah.
To get when you send it through the first time, it's only in that state. You've got no control over whether it's in the top one or the bottom one.
That's correct.
But then you just measure it at the end and then you know.
Correct. So you may get G, in which case you'll get this. You may get E, in which case you get that. Then to probe that indeed you got that state, you put a second atom through, and you see whether you get E again or G again. If you have this kind of state with this coherence in it, then you have strong correlations. If you got E the first time, you're very likely to get E again the second time. If you don't have that coherence, then if you put that in if you made a 50-50 superposition and put it through the second time, then you're going to get half the time up or down. So what is measured is the two-atom correlation function. You get E the first time, you see whether you get E again the second time. So let's take a quick peek at this, because it's not much to look at, but I'll just show you just a few things. So this is a review of modern physics from, is that a focus? So here we are. Here's the state there, just as we described it, where they talk about this as a kind of Schrödinger-Cat state. And let's see. Right, so this was the kind of phase that we just talked about, which I was calling G, or omega here is equal to 2G. All right. Wanted to just see here, but again, the point that we were raising earlier in the lecture, that the characteristic time for decoherence is shortened tremendously depending upon the mean number of photons in that cavity. That's what we were saying before. And if it's a macroscopic number, that can be a very short time. But that's not what was done in this experiment. What was done in this experiment, and again, it's the kind of experiment that we're discussing, where we have these two Ramsey zones, and the cavity mode goes into the superposition state. Now, one of the experiments that was done was the following. Suppose that we have this two-zone Ramsey interferometer. We know, you remember, as we studied last semester, that if I apply a, say, pi/2 pulse to on the first Ramsey zone, and then I apply a second pi/2 pulse, that depending on the phase of the second pi/2 pulse, if it's the same phase, then I go up to the North Pole. If the phase is different, I'll go somewhere else, and I get Ramsey fringes. Those Ramsey fringes are a function of the phase of the second Ramsey pulse relative to the first. Okay? Now, what's being shown here is the visibility of those fringes that depends on how catty the state is. When the state is very catty, when there's a big separation, big enough that it's big compared to the coherent state spread, then we see no fringes. Why is that? Well, it's it's a kind of a decoherence. It's not about the temporal decay of this superposition. This is done right after the thing happened, right? And in fact, when when the two things overlap very well, then indeed, I see these very high visibility fringes. Really, this is just the fact that the cavity state is a pointer, is a meter for whether the atom is in the excited or the ground state. What I've created is this state. If I trace over the field, and these two states are orthogonal, I have no coherence. And I see no Ramsey fringes. If these two states are very close to one another, so that there's no information inside this cavity, whether or not the thing rotated this way or that, or I can't, then the fringe reduction is not very big. This was called a complementarity experiment. Which way information is stored in the phase of rotation of a coherent state. The experiment which looked at decoherence is shown here. What's being plotted here is that kind of two-atom correlation function that I mentioned, that I didn't go through in detail, which describes whether or not you post-select, you get the excited state, you do it a second time, you get the excited state again. Okay? And they're looking at how fast that two-atom correlation function decays, depending upon whether or not they created big phase separation or small phase separation. Okay? And what they see is that the state where I have a bigger separation, I have more of a cat-like state, then I get a much more rapid decay of that pair correlation signal than here. And it's exactly at a rate that depends on that separation. Okay? So they're kind of watching the decoherence happen. Now, of course, this isn't really a Schrodinger cat. This is 3.3 photons on average. Okay? You might call it a Schrodinger kitten. You might call it a Schrodinger embryo. I'd call it a Schrodinger zygote. It's like, just a few, but it's enough still. I mean, it's a testament that shows how this kind of distinguishability, how much more rapidly you get decay. It depends on the square of that. It's 10 times faster than the decay of the energy out of the cavity. Okay. So these kinds of, this has been the form, this is where quantum optics has come from, is really putting these fundamental concepts to the test, because we have the ability to so cleanly prepare individual atoms and individual modes of a harmonic oscillator to really be able to look at open quantum systems in a very precise manner. I'll put this up, I'll link to this on the website. You can look at it more yourselves. Okay, right. So, so what we wanted to continue with then, let's see, off, not off, how off. What we were discussing as well last lecture, and I will pick up now, is the discussion of how we view open quantum systems from a Heisenberg picture. And as we discussed at the end of last lecture, it's a tricky business. It's a tricky business because if we're not careful, our open quantum systems decays away all the commutation relations. And that's not good. somehow there's something wrong with the way we're formulating quantum mechanics if after some time x and p commute. And in order to motivate that, how we deal with that, what we looked at, and we saw that there is an intimate relationship between this problem of damping in the Markov approximation and Brownian motion. So where we were last time in discussing that was to look at the classical problem of Brownian motion, in which we imagine we have a fluid and we have this impurity that is wanting to move through this fluid, which experiences viscosity. And that damping, we said, was due to the fact that, as originally conjectured by Einstein and studied by Einstein, that this kind of damping was due to the collision of the impurity with many, 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 many molecules that make up motion. And also, these collisions not only lead to damping, but they lead to the random Brownian trajectories that Brown observed in whatever it was, 1827. I actually found out Brown was a botanist. I didn't know that. He's a very famous botanist. What?
He was looking at pollen.
Yeah, he was looking at pollen, right. And I guess he thought that maybe there was something organic that was going on inside this.
He disabused himself of that very rapidly.
Right, yeah, but at first that was the idea. Okay, so what we discussed was that the way we look at this is to say that the equation of motion for this, say, pollen particle in the molasses was there's some time-dependent force, and we broke up that force into something which is the average over the statistical ensemble of possible forces, and a fluctuating force. Okay? So this force is a stochastic force. It's stochastic in the sense that we are not keeping track of all of the impacts that the individual molecules of the fluid make upon my pollen particle. We just know something about the statistics of that force. And what we know is averaged over all of the probability distribution of possible forces, that this force has mean 0. And we take the Markov approximation and say that the force is only correlated with itself at extremely short time scales that we effectively take to be a delta function. At any times appreciably different from the correlation time, which is essentially 0, there's no correlation between what force it's feeling at time t and a slightly different time. Okay? And the mean force gives rise to viscosity, or damping. Okay? So, our equation of motion takes this form which Langevin wrote down after Einstein, the sort of reformulation of Einstein's statistical approach. This is what we call a stochastic differential equation. And we can integrate this equation. Now, it came up at the end of last lecture. The integral I'm about to write down is just the integral regardless of whether this is a deterministic force with a well-known function of time or a random force. Let me ask you, how do you integrate this equation? How do you write a formal solution to this? Well, what I have is, if I didn't have this term, that I know how to write down, right? That's just a damped exponential damping. This is a source term. So I need to write down the Green's function for the system. And that's easy to do. So that tells me that this is the homogeneous solution. That's if I had no force. And then I have the convolution of the Green's function with the source. And what's the Green's function for that equation? Well, it's just an exponential itself, right? Minus gamma t minus t prime. So that's just the solution, stochastic or otherwise. All right, so from this we see that the mean momentum as a function of time averaged over, this is averaged over the reservoir, that is the statistical distribution of possible forces that are imparted upon the impurity, right, it decays. That's fine. And then I have, and that's it, because this has mean 0. Okay? And we can look then at delta P, which is P minus the mean. And that is random. That's given by the integral from T0 to T. dt prime e to the minus t minus t prime, the force. So the fluctuations in momentum averaged over the reservoir are equal to this double integral okay? And this is equal to this coefficient 2d, as it's traditionally written, times the delta function. And so we get 2d, the integral 0 to t dt prime, e to the minus 2 gamma t minus t prime, or 2d, or d over gamma, 1 minus e to the minus 2 gamma t minus t naught. So what this, the Langevin equation tells us is two things. Firstly, on average, the momentum is damped. But in addition, there are fluctuations around that average, and those fluctuations change as a function of time in this manner. And in particular, at short enough times, when the time is small compared to the damping time, then what we see is that this spread increases linearly with time. That's not surprising. That is diffusion. Do you have some diffusion? right? And so the net effect of these random collisions of these thermal particles with the pollen are twofold. One is to cause damping of the motion, but also to cause the motion to diffuse away from its mean value. In the long term, when this is much, much bigger than 1, then, well, this thing goes to equilibrium. And if the reservoir is at temperature T, then we know from the equipartition theorem that P squared over 2m goes to 1/2 kT. So that means that in the long term, these fluctuations in steady state go to m k Boltzmann T, which is equal to the diffusion coefficient over the damping rate. And so from this we derive the fundamental fluctuation dissipation theorem, which says that there is an intimate relationship between damping and diffusion. The diffusion coefficient and the damping coefficient are related to one another, and in the simple model, that's their relationship. And that, again, is not surprising from the point of view of the fact that both physical effects are arising from the same kind of interaction. One is a kind of average effect, and one is an effect that is fluctuations about the average, and that was known as fluctuation dissipation.
I have a question.
Yes?
You've done this in one dimension, and 2 and 3 dimensions can introduce in many problems tremendous mathematical difficulties, qualitative difficulties as well. Is that true for this equation, or is this truly representative of 3
I
dimensions?
think this is truly representative. I don't think that there's anything particularly odd that happens. I mean, there are, I agree, lots of cases where what you get in 1D is kind of anomalous, and what happens in higher dimensions can be quite different. But I don't believe that that's true in this circumstance. All right. So with this knowledge in hand, let's turn to the damped simple harmonic oscillator in the quantum problem, which has this intimate relationship with Brownian motion, sometimes known as quantum Brownian motion. So, what I want to do is say, let's look at the our damped simple harmonic oscillator that we study now starting from our fundamental coupling of the system oscillator coupled to the bath of oscillators. This was the model we used in our derivation of the Lindblad master equation for the system oscillator. Thought of as example, a cavity which can decay through the mirrors. And the Hamiltonian is a very simple one that we use to describe this. We have the cavity Hamiltonian, we have the Hamiltonian for the collection of bath oscillators, and then we had a linear coupling between the bath oscillators and the simple harmonic oscillator of the system, whereby I can annihilate a photon out of the system and create it in the bath, and vice versa in the rotating wave approximation that we like in quantum optics. Okay? So now what I want to do is a Heisenberg picture. I want us to look at the evolution of these operators in the Heisenberg picture. So, we got that. Do an H bar because I left it there. And I get minus I omega naught A plus sum over J, G sub J, minus I, Bj. And the bath oscillators evolve in time. I get the free evolution of each oscillator, and then I get minus I star A. Okay? So now I have a couple set of linear ODEs, and I can manipulate them. I can do some formal solutions and substitutions and all the goodies that we did sort of when we looked at this in terms of probability amplitudes in the past in a Wigner-Weisskopf type. But let me just, we can write down a formal solution here. It says that dj at t is equal to e to the minus I omega jt dj at 0 minus I gj star integral from 0 to t dt prime e to the minus I omega j t minus t prime a hat prime. That's again using a Green's function. Take the derivative, you'll see that works. Okay, so now what I'm going to do is to make life simpler, I'm going to go to a rotating frame. It's equivalent to a kind of interaction picture. Let me define A of t as the free evolution and then a slowly varying envelope. Okay, so my envelope, this is an operator 2. Just, I'm not going to keep a hat on it, I'll put a tilde on it, is e to the plus I omega naught t a hat t. So a tilde dt is equal to plus I omega naught a tilde plus e to the plus I omega naught t d a hat. Okay, so now I just plug back in over here. And I get, so that gets rid of the free evolution, and I get minus I sum over G over J, G sub J, dj of t e to the plus I. Okay. And now I plug back in this solution. And I get the following. Minus the sum over j, the magnitude of the coupling constant squared, the integral here to t, dt prime, e to the minus I omega j minus omega 0, t minus t prime, a tilde of t prime. That's from this term. And then I get minus I sum over j g j e to the minus I omega j minus omega naught t vj. Here. Okay, so let's see. I think that's all good. So what do I see from the form of this? Well, here's something that's acting on the mode operator, and here's something that only depends on the bath. Doesn't depend on the system. This operator here, I'm going to call f hat. It's a bath force. Okay, let me double check my notes here. Yeah, looks good. Okay, so now we've seen these kinds of integrals before. They're always messy. There always seems to be a ton of hand waving, but I'm not going to wave my hands through it again. I'm going to assume we can do it and make the Markov approximation, which means basically send this t to infinity. Go back, think about Wigner-Weisskopf. We've done it before. Okay? In which case, this thing becomes the pi times a delta function. It's half a delta function because it goes only from 0 to 2 minus instead of 2 pi. And this thing becomes a delta a t when we take it outside the interval. So that's the same kind of Wigner-Weisskopf approximation that we've done before, which is effectively the Markov approximation. When we do that, and we remember that this sum with the delta functions in it that 2 pi times this equals 2 pi, the integral over the density of states that's what we call kappa. It's like the Einstein A coefficient. So, in the Markov approximation, our Heisenberg equations of motion have an irreversible form. Not down in my cap part. This is what we call the quantum Langevin equation. This equation has the same kind of form that we saw for the Brownian motion. There is a mean effect, that is the damping of the mode. But in addition, there's a fluctuating force. In this case, that fluctuating force is coming from the quantum fluctuations, generally speaking, coming from the back modes. What do we know about this operator? Well, let's take the bath to be a thermal state, as we have in all our studies of this kind of open form system. What is the mean value of this bath force averaged over the bath? Well, that's equal to to make math doesn't really matter. What's that?
0.
0, right? It's a thermal state. Thermal state has no mean field. Same thing is true for F dagger. Okay. This is J. In contrast, if I look at, say, F dagger, or F squared is 0 as well, and any power of this non-remission operator has no mean, right? There's B squared also, or B dagger squared. However, if I look at, oh, I shouldn't have erased it, but I guess we can figure it out. F dagger, say, T, F with T prime. Okay. Well, what's that going to be? Again, I only get when I have a thermal state, only when I have equal numbers of B and B daggers in the same mode is the mean going to be anything other than 0. So the sum collapses to a single sum. I get GJ squared. I get e to the minus I omega minus omega j, T minus T prime, B j times equals 0. And this is the mean number of thermal photons in the mode. J. And this, in the Markov approximation, is what we showed was equal to gamma times the delta. And we do the same density of stage trick and Markov approximation. So in the Markov approximation, what we see is that this correlation function is delta correlated with this diffusion coefficient. Similarly, the dagger and the other guys, well then I'm going to have, in this case, the same thing, except I'm going to have a V dagger. And that is n bar plus 1, because I do the commutator. Okay. So, what we have is something that looks just like the Brownian motion problem, with damping and what's called the Langevin force, the fluctuating force. What I want to show now is that this fluctuating force rescues the commutation relations, rescues the fact that we don't just decay the fluctuations in this mode, but we replenish them with a fluctuating force. Without this term, we would just find that the mode A would decay and the fluctuations in mode A would go to 0. We need the source in order to replenish that and maintain the quantum case, even at 0 temperature. And there's that, well, that was a half plus 1, sorry. So let's write down a couple of things. So we can, as the same way that we integrated the Brownian motion, I can integrate I'm sorry, you'll excuse me, I keep writing gamma when I need to write kappa, because I have it 2 different ways in my notes. But for the case at hand, this is kappa. So we can integrate this just as we did for the classical Langevin equations. There's no difference. Okay. The expected value of this averaged over the reservoir is the decaying mode, just like we had when we looked at this same equation of motion based on the Lindblad equation. We saw that the mean field decayed on average. But now let's look at the fluctuations. In particular, let's look at the commutator. Of this Heisenberg operator with the dagger at equal times. Okay. So that's equal to e to the minus kappa t, the commutator of that with its dagger. Plus term, I'll write this out, plus I'll commute t dt prime 0 t double prime e to the minus kappa over 2 t minus t prime e to the minus kappa over 2 t minus t double prime, the commutator of f at T prime with F dagger at T double prime, plus terms that depend on the commutator of A with F. A0 to F. And F dagger. However, these guys commute, right? Because this is, at time t equals 0, the bath oscillators and the system oscillator commute. And this thing only depends on the bath oscillator at time t equals 0. So these commute. What about this? Well, we have to write all that down, don't we? This is equal to which is 1. And so this becomes kappa times the from the same factor. So what we see here is the following. Putting that all together, this commutator is 1. The delta function t minus t prime makes these guys equal. I'm going to factor out another e to the kappa t. And I get the integral 0 to t d t prime kappa e to the minus kappa t. Which is equal to
that is plus, right?
Plus, thank you. Very important.
That's prime, t prime, right?
And t prime. Yes, t prime, indeed. Thank you. Which is equal to e to the kappa t minus 1. So that this commutator at all times is 1. Phew. So, this commutator saved the fact that fed in, otherwise these fluctuations would decay. Another way we look at this, and I'll just conclude here, is if I look at this, I can think about this the following way. My output mode after the time t is some factor, I'll call it L, plus noise. This is what's called Langevin noise. This is a kind of expression, this is the in, let's call this in. This is the kind of input-output relation we've seen before. Suppose I have a beam splitter. A beam splitter is an attenuator. If I send a laser beam on this beam splitter, whatever amplitude I have here, it's attenuated. There's a square root of a transmission coefficient, say. So the field is attenuated. However, quantum mechanically, we have to be careful. Because just because we attenuated it, if I started with a coherent state, which is my E, and I attenuate it, if I started with quantum uncertainty, if I don't do something, I'll attenuate everything. I'll attenuate the uncertainty as well. So this is not unitary. It's not describing the real physical world. Because whenever we attenuate, there's also got to be another mode. This is the bath, which is the reflected mode. And vacuum fluctuations entering from the unused port must be there in order to replenish. In fact, if I were to write a simple input-output relation, this is A in, this is B in, then A out is equal to the transmission of A in plus the reflection of B in. This is my noise operator. This is the simplest example of the Langevin effect, whereby attenuation and fluctuation are intimately related. In this case, solely the vacuum noise. What we just did was a much more complicated version of this, but this is the essence. Whenever you have dissipation, you must also have fluctuations. And in the quantum world, that's particularly important if we want to think about things like uncertainty states. So just to conclude this one last statement, it's quite often the case when we're dealing with open quantum systems that it's trivial to deal with them in the Heisenberg picture. If there are certain observables that we care about, we could just write down almost by eye, without writing a fancy Lindblad master equation, what the input-output relations are and what the noise operators have to be in order to preserve the commutation relations. And so quite often you'll see in works, in public literature, this is the simplest way often that one deals with open quantum systems. It's not universally convenient because if I care about things beyond, say, the quadratures, then I'll have to write down a different set of Heisenberg equations of motion for every different observable, and there'll be different kinds of noise operators. But if I know exactly what I care about, then it's typically the easiest thing to do. And something to keep in mind. Yeah?
Does this depend upon the correlation times or the different time scales of the process?
Yes, indeed. So everything that we talked about in the context of the derivation, the Born-Markov approximation, and the separation time scales was all swept under the rug here and assumed. When you write down this, you're making some very radical kinds of approximations. But in this case, they're very good approximations, whereby the correlation times of the reservoir are tiny compared to the decay rate of energy out of the cavity, for example. So it's all the same physics that went into the Schrodinger picture derivation of the Lindblad master equation is buried in here as well.
So this fits into a multiple time scale.
Kind of integration,
Kind of
yeah.
integration, yeah. I noticed years ago that people that were studying spacecraft orbits had to make massive use of this kind of approximation because of its tiny fluctuations.
Right.
Interesting.
All right, very good. Let's conclude there. What we're going to do for starting on Thursday and probably following through to the end of the semester is talking about the theory of quantum trajectories and continuous measurement. So, after a while.